So we've talked about how you can use support vector machines or other machine learning techniques to build a model. That raises the question, does the model work? We can take a new example, put that example in the model, and then get the result of the model's prediction back. In this case, it says don't count on it. But can we actually trust the predictions from the model? Let's go back to the example where we're using a high C to train our support vector machine. In this case, we put the decision boundary between an orange point and its immediate neighbor, the blue point, and this perfectly classified all of our examples. The way we would talk about this is we would say, this gave us a training accuracy of 100%. Essentially, everything we used to train the model, we predicted correctly. Training accuracy is part of the story, but it's not the whole story. We'd also like to see how the model does on data that it hasn't been exposed to for training. So now if we had a separate set of data, we could actually overlay those data onto the same model and get predictions. So the bright orange and the bright blue points are data that the model never saw when it was trained. We can then evaluate accuracy on these points, and that gives us something called a testing accuracy, because the model was able to correctly get these 5 orange points as well as these 2 blue points. It got 7 predictions correct, but it also missed 3 predictions. So it has 7 out of 10 correct, therefore it has a 70% testing accuracy. If we go back to the case where we had the medium C, so this is the model that didn't quite get everything right. It misses this one orange point here, but it gets the other points right. It's giving up the ability to get every point right during training, but it gets this larger margin in return. That way, when we assess its training accuracy, it's not quite as good. For instance, because it got this orange point wrong, its training accuracy is only 92%. Less than the 100% that we observed with the very heavily fit model, the high C model. But when we overlay our test points on it, we can see that this model actually perfectly described our testing points. Therefore, this model would have a testing accuracy of 100%. And we can think about the other condition that we also talked about when we were discussing C, the low C condition. So this is the model that maximizes the margin between the points even more. So it's ignoring even this point. In this model, the training accuracy is the same, so it's also 92%, and our testing accuracy is also 100%. Overlaying data that the algorithm has never seen before allows us to predict how the system will do in new data, because we can fit the data we have very well, but when we do that, we're sometimes giving up the ability to generalize to data that hasn't been seen before, and that's really what we care about. We want to be able to predict the things we don't already know. At the end of this, we could make a table where we compare the training accuracies and the testing accuracies of the various C parameters. In our highest C case, we achieved perfect training accuracy, but we only achieved 70% testing accuracy. While as in the medium and low C cases, the training accuracy was a little bit lower. We weren't doing as much to fit the data that we already had, but the testing accuracy is much higher. And this is a trade-off that you start to see. Models will become what we call overfit. Namely, their training accuracy is very high, but their testing accuracy may display a substantial drop-off. So the high C model here we would say is overfit. The medium and low C models, because the training accuracy and testing accuracy are similar, we would say are not overfit.